When you're collecting data, it's good to have some way of organising your results. So a frequency table is a really handy way to do that. It just really shows how many times something happened, because that's all frequency means. How frequent was it? So, as an example, if I asked all of you guys how many brothers and sisters you have, and I go around the class and I say, well, these are the options, 0, 1, 2, 3, or more than 4, then I can take a quick tally so that as I get my results in, I can just make a running tally, and I'd probably do all of this first. And in case you haven't seen it before, that gatepost method, 1, 2, 3, 4, and then the fifth one is a gatepost, helps you add things up quickly. At the end of doing my survey of the class, then I'd say, right, what were the results? Okay, we had 2 people here, 6 here, 7, and just writing them with numbers is a nice way to finish off, because that is much easier to read than the tally, but the tally is a really handy way to record it. At the bottom, you can even include the total there, or the sum, and see that there was 20 people in this survey. Now you'll notice that I might have grouped some people together, and that's because if I had a table that went on for 4, 5, 6, 7, okay, sure, someone might have 12 brothers and sisters, and I've lumped them all in together with the people who have 11 or 13, but sometimes you've got to make a sensible decision as a researcher about what you might make a group for, so that you don't have a table that goes on crazily forever. Now, once we've got our frequency data sorted, there's 2 ways that we can display it, either with a column graph or a histogram. Now, lots of people get these mixed up, but once you understand the purpose of them, it's quite easy to see the difference. So they're both used to display grouped data, and the reason that we've got to group it sometimes is so that we can get sort of a cluster of things that are alike together. Now, sometimes that means we've got to make a little bit of a compromise on things, as you'll see in these examples. Now, let's look at the column graph first. It's used for discrete data. Now, remember, that's data that's got numbers in it, but it's like 1, 2, 3, 4, things that you can count generally. Or it can be used for categorical data. And the key thing about it is there's gaps in between the columns. So I just remember a column graph, it's got columns that look like individual columns, whereas the histogram is the other one. It doesn't have any gaps. Now, I've got one here for eye color. So let's pretend that we've just surveyed everybody in the class to find out if they've got brown, blue, green, or grey eyes. Now, straight away, there's a problem there. I've grouped people, haven't I? What if your eyes are bluey grey and we can't decide which column to put you in? Well, that's one of the limitations of clustering things, isn't it? That you sometimes lose that detail. And statisticians have to make decisions about whether someone's eyes are more blue or green, and other people might not agree. So it can be a little bit subjective. Now, you always put frequency down the side for all of these graphs. So frequency is how often did this happen? So if you're doing a survey and you've got those tally marks, these are your numbers. So here, I can also read things off the graph and say, hey, there must have been 8 people who had brown eyes. Looks like there were 6 people with blue, 4 people with green, and looks like about 2 people with grey eyes. So if I wanted to, I could easily work out how many people were in that sample by saying 8 plus 6, that's 14, plus 4, that's 18, plus 2, there must have been 20 people. So you can get quite a lot of data from that. You can also see at a glance that brown eyes is the most common thing for this group. And that's the main virtue of a column graph or a histogram. In an instant, it should give you valuable information about what was the most popular or the most common. So eye color is an example of categorical data because the data is categories, it's not numeric. How do I decide how to organize these columns? Well, I just picked a method. They could be done lots of different ways. Here I've got discrete data. Let's pretend that I've asked everybody in the class how many pets they have. And everybody just happened to have between 0 and 3 pets because I didn't want to do a really big column graph. Okay, so again, I've got the frequency here. I can see that 2 people had no pets. 3 people had 1 pet, 5 people had 2 pets, and 2 people had 3 pets. So these numbers along the bottom was the answer they gave to the question, how many pets do you have? And these numbers up the side, that was how many people put their hand up for each option. Does that make sense? All right, so that's column graphs. Now, histograms are just like column graphs, except that you use them for continuous data. And that should make sense for why there's no gaps in between. Have a look at this example of height of people in the class. And I've just done an imaginary survey here, pretend that we've measured everybody. Now you can see that I have grouped the data. Okay, I have to group it because if I put a single column for every single person, then I've got to decide the cutoffs of I've still got to group people somewhere, either people who are all the same centimetre or all the same to the millimetre. It'd be a nightmare. So instead I've grouped them just with sensible sized groups. Now it's up to you how you group the data. Some people might have grouped these every 5 centimetres. I've gone for columns every 10. Okay, so everyone who's 150 something centimetres is in here, and there was 3 of them. Again, the frequency here is here. Everyone who was 160 something is here, and there were 7 of them. Now, there's 2 small issues to think of here. What if you were exactly 160 centimetres? Does that put you in this column or this column? So you could have the exact same data, and 2 different students or statisticians could have a slightly different histogram. Now, it's up to you if you put those people on the boundary cutoffs in that side or that side. Just make sure you're consistent all the way along. So if 160 centimetre person, you put them in the next column. Then if you had a 170 centimetre person, by rights, they should go in the following column. Does that sort of make sense? Now can you see why there's no gaps in the columns when you've got continuous data? It's because in between being 150 something or 160 something centimetres, there's nothing in between. People roll straight from one of these groups into the next. And it would be wrong to have a space between, because it would imply that these people are really different from those, when really we've just decided where we want to make the cutoff, and we've made a cutoff, but we don't want a gap. Now, once you've graphed your data, there's a couple of situations that could happen. Your data could be symmetrical, or it could be what we call skewed. So symmetrical data looks something like this. Now remember, what we're measuring on the y-axis is frequency, or how frequent something was, how often it happened. So with symmetrical data, the most common thing to happen tends to be in the middle of the distribution, and then you've got less common things further away. And this happens a lot. For example, if we measure how tall everybody is in the class, they'll tend to be a middle sort of height that a lot of people are. And being really tall or being really short is a lot less common, isn't it? Now, skewed data has the most common results either being towards one end of the distribution or the other. How do you remember which one is which? Well, I tend to just remember that positively skewed data starts out with really positive results or really high scores, and then they get lower and lower. And negatively skewed data starts out with quite small scores that then get bigger. So it starts with what the name sort of suggests.